2, 1. All right, we're doing it again. Here we are, Math 2070. We are now talking about solution sets of linear systems. Okay, so let's jump right in. So I set this up last time. So a homogeneous linear system is a system of linear equations that can be written as the following matrix multiplication. So as we talked about last time, every system of linear equations is really a matrix multiplication in disguise, and as we noted, any matrix times a zero vector gives me 0, so these systems are quite nice because we know they are always consistent. They always have at least one solution. So that takes care of one of the things we're interested in when you have a system. Does it have an answer, yes or no? And here we see that if the right-hand side is 0, then yep, you've always got a solution. Now, it's kind of trivial, so anything that is non-zero, we'll call that a non-trivial solution, and this x equals 0 we will refer to as the trivial one. So let's actually look at a homogeneous system and talk about what the set of solutions is going to look like. Okay, so this system here can be rewritten as ax equals 0, where a corresponds to the coefficients, and we'll take our peepers out here and make sure that I didn't screw this one up, and it looks safe, looks good. We're copacetic. Our vector x corresponding to the unknowns, x1, x2, and x3. And again, noting that we have 3 unknowns, so 3 columns, and 3 equations, so I have a beautiful 3 by 3 matrix, multiplying an element of R3, so the dimensions are good. Now we go ahead and set up our augmented version of this by, again, this matrix going on the left and the right-hand side going on the right. And here we can reduce echelon form it and get this matrix here with some unfortunate fractions, although I'm a big fan of this number. And from here I can read off that x1 plus 17 eighths x3 equals 0, and x2 minus 3 quarters x3 is equal to 0. So we see that x3 is a free variable. There was no pivot column in the third column. So I can get x1 and x2 in terms of these. And in particular, note this reveals that I have got some non-trivial solutions. If I plug in 8 for x3, I can then get x1 and x2. And while I can, of course, plug in numbers for x3 and give you more numbers, it's a much better way. A much better way of revealing the solution set to you would be to sort of generally write this out. So note x1 I can solve for it in terms of x3, x2 I can solve in terms of x3, and x3 is just x3. And now note x3 is appearing in every entry, and as we discussed, scaling a vector just means multiply all the entries by that scalar and we pull it out. And here we see that if I set x3 equal to t, the sort of parameterization that we've done before, and v equaling this vector here, then the set of solutions to ax equals 0 is just the span of this vector v, the collection of all linear combinations. And in this case, we'll call this solution the parametric vector form. All right, this is a much nicer way of writing these solutions. We know the solutions need to be vectors. We're trying to find x that satisfies it. X is a vector. And here we see that there is a particular vector, and all scalar multiples of it will give you the set of solutions. Pretty cool. All right, so that took care of the case of homogeneous systems. What about the case of non-homogeneous systems? All right, so we're looking at ax equals b now, where b is potentially non-zero. Well, let's just jump right into an example and work it out. So again, a beautiful 3 by 3 situation, 3 unknowns. Note x1 does not show up to the party in the third equation. Double check all the numbers, everything seems to be good. Alright, we set up our augmented matrix, we perform our row reduction, and here we go. We have a big fat row of zeros at the bottom, and note no pivot column in the rightmost column, so we are good, we are consistent, and in fact I can read off some solutions to you here. This first row tells me that x1 minus 5x3 is equal to negative 2, and x2 plus 2x3 has to equal 1. And pulling apart the solution similar to how we did last time, I can solve for x1 and x2. And here I have this sort of constant vector showing up, and here I've got this linear combination of all of these, the scalar multiples of all of this one particular vector, 5, negative 2, 1. And if I let P equal this particular solution right here, and V equal my term showing up here, we get the set of solutions in this parametric form as a vector P plus T times some other vector. And it is worth noting here that this has to be the solution, so when I multiply this by A, I need to get the 0 vector, and the vector B, and the only way that could possibly work is, well, all of these need to multiply out by 0. So in particular, we see here that P is a particular solution, hence P, to the system, AX equals B, and V is the solutions corresponding to the homogeneous system. And if you've taken differential equations already, this is hopefully looking a little familiar to you. So indeed, every homogeneous system, when you solve it, AX equals B, you will get solutions where one of them will be a particular solution, and then the others will be the solutions to the homogeneous case. Pretty neat. Alright, so that takes care of what solution sets are generally going to look like for systems. Now, with all of this under our belt, in the next video, we will look at a couple quick little fun applications of all of this stuff. So, I'll see you next time.